Here's a problem I made up, and I've never worked this kind of problem before, so I've been having some fun here figuring it out. A 250 gram mass stretches a spring by 4 centimeters. The damped frequency is 2 hertz. What is the coefficient of resistance? So we might want to measure that coefficient with the material we make a spring out of. And I threw the word damped in there because I didn't want there to be confusion. I'm not talking about the natural frequency of the spring before you consider the coefficient of resistance. This is the true frequency of the spring with this mass attached to it. And so we have to first decide, are we going to work in meters or centimeters, or are we going to work in kilograms or grams? And I'm going to be consistent, work everything in terms of kilograms and meters. That's because I know that the gravitational acceleration is 9.8 meters per second squared. So if you work with that, let's go with kilograms and meters. So 250 grams is 0.25 kilograms. It was 1,000 grams in a kilogram. And 4 centimeters would be 0.04 meters, 4/100ths of a meter. So we need those conversions there. Otherwise, if we just throw these numbers in and use G as 9.8, we're going to be in trouble. It's not going to work out right. Okay, frequency is 2 hertz. That means that if we get the spring vibrating, it's going to go up and down 2 times every second. About that fast. And pretty good at that, because 2 times per second, as a musician, if you play 2 quarter notes per second, that's 120 per minute. That's the metronome marking of 120. It's allegro. And you think, well, let me see, Stars and Stripes Forever. Bum, bum, ba, da, bum, ba, 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 bum, ba, dum, ba, dum, ba, dum. That's about 2 per second. So it's bouncing up and down twice per second. I don't know if that helps a bit in this problem. Probably not. But anyway, I just thought I'd throw that in there. Okay, well, our equation is y double prime plus 2r y prime plus omega squared y equals to 0. And the solution to this, let's see, what is it? It's y of t is equal to, I'm going to work the solution because I'm not quite sure I'm going to get that off the top of my head so well. So let me work this out real quick. The characteristic equation is m squared plus 2rm plus omega squared equals to 0. So m, the roots would be minus 2r plus or minus the square root of 4r squared minus 4 omega squared divided by 2. And that would be minus r plus or minus square root r squared minus omega squared. Well, if this spring is executing underdamped phenomena, if it's underdamped vibration, then this is negative. And so if this is negative, this would be written as minus r plus or minus I times the square root of omega squared minus r squared. I'll reverse those to take care of the negative. So this is the underdamped situation where omega squared minus r squared is positive. So that means my solution y of t will be c e to the minus rt. So the real part ends up here, minus rt, times, wow, do I have sine or cosine? I just write cosine, but if we're writing cosine, then it's going to be, well, it's going to be this number times t, so square root omega squared minus r squared times t plus delta, the phase shift number. Okay, so here we go. This gives us our will lead to our frequency. And to get frequency, I'm going to have to figure out what omega is, aren't I? And r squared. So the omega, I may need more information up here to do this problem. Let's think about that. The frequency is this number, square root of omega squared minus r squared over 2 pi. It's a reciprocal of period. Period is 2 pi over the coefficient of time. Frequency is a reciprocal. So frequency is this, and that's equal to 2 hertz. So square root of omega squared minus r squared is equal to 4 pi. Great. All right. Well, which makes omega squared minus r squared equals to 16 pi squared. Well, that doesn't resolve my situation here. So I'm in a quandary. What information will I need that I can gather that will give me the coefficient of resistance? Because I don't know what omega is by itself. So I'm going to think about that and come back to you. Well, as soon as I shut the camera off, it hit me how I can get r squared and how I can get omega. I haven't used this information yet. The 250 gram mass stretches the spring by 4 centimeters. That's how we can get to omega squared. So I'm going to do a little erasing. Alright, so we're back to an early relationship we worked with. The weight, which is mass times gravity, is equal to K times L. And L is 4 centimeters or 0.04 meters. So the mass was 0.25 kilograms. Gravitational pull is 9.8 meters per second squared, so I just write 9.8. As long as I'm consistent with kilograms and meters, my number is going to work out nicely here. 9.8 is equal to K times 4 centimeters is 0.04 meters. So K is equal to, and let's see, I feel like I've done this before. Maybe when I tried this video earlier. Isn't it 61.25? Yeah, it is. I got it on my calculator. 61.25. Okay. So that's great. Is that really what I want to know, though? Because we don't really have to do that, don't we? I keep forgetting this. Omega squared is G over L. That's all I had to look at. So G is 9.8. The length is 0.04. So omega squared is 245, I think. 9.8 divided by 0.04. 9.8 divided by 0.04 is 245. Okay, so there we go. After all that quandary, I realized where I could get omega squared, and I didn't have to solve for k. I just seems like I keep doing it though. So we can figure out r squared now, and omega squared is 245 minus r squared is equal to 16 pi squared, and so it makes r squared equal to 245 minus 16 pi squared. And I sure hope that's positive. If not, I'm going to have to explain something. Alright, 245 minus 16 pi squared is about the, oh, no problem, it's about the 87, roughly. About 87.1. So r is the square root. I'm using all my decimals, so take the square root and it's about 9.33. Okay, now, so we know what R has to equal to here for this spring. And finally, the question was, what is the coefficient of resistance? The coefficient of resistance is 2 times mass times R. So it'd be 2 times 0.25 kilograms times my R number, 9.33. So that would be about 4.67. I think the units were hertz, weren't they? Now I'm going from memory. I think they're hertz. But anyway, 4.67 is the coefficient of resistance here. So we can figure that out, can't we? And it didn't take much in the way of measurements to do so. We just needed the mass, how far it stretched it beyond the natural length, and also that the damp frequency was 2 hertz. So okay, well, let's move on.